When an asteroid struck the Yucatán Peninsula in Mexico about 66 million years ago, it set off an extinction event that wiped out the dinosaurs and ended life on Earth. The Chicxulub crater, which is 100 miles wide, was left behind by the impact, which had the same energy as 100 million atomic bombs. A city-sized asteroid smashed through Earth's atmosphere 66 million years ago, crashing into the shallow waters off the Yucatán Peninsula in the Gulf of Mexico. The cosmic artillery bombardment carved a 100-mile wide crater in the Earth's surface, ejecting plumes of vaporized rock and debris into the atmosphere that obscured views of the sun for years or even decades. Following the initial blast, the diminished sunlight caused the Earth's surface temperature to plunge by up to 28 degrees Celsius, contributing to a global extinction that destroyed 75% of all life on Earth. But the dust gradually settled. In the 1980s, scientists discovered evidence of asteroid dust strewn over the world inside the same geological strata that corresponded to the dinosaurs' extinction. Chicxulub crater was discovered in the Gulf of Mexico, and because the crater appeared to be the same age as the worldwide rock layer loaded with asteroid dust, researchers were very positive that they'd figure out the story of dinosaur extinction. The most recent evidence comes from rock core samples taken from Chicxulub crater, which lies beneath the bottom in the Gulf of Mexico. Researchers believe they've discovered a telltale indicator of asteroid dust in the most current analysis based on these samples, which were gathered during a 2016 mission co-led by the University of Texas at Austin. It takes the form of iridium, which is abundant in some asteroids but scarce in the Earth's crust. A sample retrieved from the crater's peak ring included the largest quantity of iridium-peppered rock, as well as a mixture of ash from the impact and ocean silt. This sample also has high quantities of other elements associated with asteroids, resulting in a chemical fingerprint that resembles asteroid dust seen around the world in the 1980s, and closely fits the geological site of the impact event. The Chicxulub crater is one of the most massive impact formations yet discovered on Earth. But there's something else unique about this effect. The crater appears to have been formed by a carbonaceous chondrite asteroid, which is a black rock rich in organic compounds. This is unusual because impacts from this type of object are uncommon. They only account for 5% of all meteorites collected. So how come an asteroid caused one of the greatest craters on Earth, and the impact that killed out the dinosaurs? David Nussbaum and his colleagues at the Department of Space Studies Southwest Research Institute in the United States have been working hard to solve this riddle. They created a computer simulation of how objects in the main asteroid belt's orbits can be dislodged and become near-Earth asteroids, with the potential to collide with our planet. Their model included approximately 42,000 asteroids in the main belt, with widths more than 5 kilometers, as well as how they are affected by factors such as solar radiation pressure and Jupiter's gravity. They calculated that Venus and Earth receive around the same number of asteroids larger than 5 kilometers, with Mars being impacted roughly 3 times fewer. Interestingly, Nussbaum discovered that almost 6% of the simulated Venus impactors had evolved into a retrograde orbit prior to impact, which is akin to vehicles colliding head-on with a far higher impact speed and hitting the planet at an astounding 220,000 kilometers. But what about the greatest impactors, such as the Chicxulub asteroid? Because of the orbital mechanics involved, Nussbaum and his colleagues discovered that the smaller impactors, less than a kilometer in diameter, are most likely to have come from inner border of the asteroid belt, and so have an ordinary stony composition as found in most meteorites observed. The greatest impactors that have impacted Earth, however, are more likely to have come from the middle or outer asteroid belt. They believe that the impactor responsible for the mass extinction 66 million years ago was a main belt asteroid that most likely originated outside 2.5 astronomical units. An astronomical unit is roughly the distance from Earth to the Sun and equal to 93.2 million miles or 8.3 light minutes. The impact was devastating, causing tsunamis to draw on enormous sections of shoreline and firestorms to flare over the planet. The collision also hurled massive volumes of dust and molten rock into the air, which, coupled with soot from all those flames, obscured the sun for an extended period of time. To make matters worse, much of the vaporized rock was sulfur-rich, resulting in sulfuric acid aerosols that rained back down on Earth, acidifying the oceans. The asteroid that caused all of this destruction is long gone, almost completely obliterated in its kamikaze attack. However, scientists have been able to measure it to some extent over the last few decades. After noting that 66-million-year-old clays around the world contain considerably more of the rare metal iridium than the layers above and below them, by a team led by Nobel Prize-winning physicist Luis Alvarez, suggested the death by above hypothesis for the KT extinction in 1980. The iridium was most likely supplied by an impactor that impacted Earth at the time, according to the scientists. A decade later, another study team discovered the impact site, a buried crater about 90 miles wide that straddled the Yucatán Peninsula and to the Caribbean Sea. However, not everyone agrees. Some scientists believe Chicxulub crater was destroyed by a comet. Scientists also calculated that roughly 1/5 of all long-period comets are frozen wanderers that take more than 200 years to complete one orbit and shatter as they pass near the Sun, resulting in a large number of fragments. This population might increase by an order of magnitude the impact rate of long-period comets capable of triggering Chicxulub impact events. This new rate is commensurate with the age of the Chicxulub impact crater, offering a satisfactory explanation for the impactor's origin. Chicxulub's crater's dimensions, around 100 miles broad by 12 miles deep, give us a rough estimate of the impactor's size. Scientists determined that the incoming object was most likely 4.3 miles broad. But that's probably not the figure you're thinking of, because it assumes the impactor was a fragment of a long-period comet. Because asteroids in the main belt between Mars and Jupiter circle more slowly than long-period comets, they must be larger to carve out a hole the size of Chicxulub in the Earth. The asteroid camp believes that the impactor was around 6 miles in diameter. The cosmic rock, whether an asteroid or a comet fragment, was large enough to cause one of Earth's 6 known mass extinctions. A team of scientists, led by Bill Bottke of the Southwest Research Institute in Colorado, proposed an origin story for the dinosaur-killing asteroid in 2007. A massive collision in its innermost portion of the main asteroid belt around 160 million years ago that broke apart a 106-mile-wide space rock called Baptistina. Fragments formed by the collision were slowly carried to orbits, where they may strike the terrestrial planets by dynamical processes. The researchers said in a 2007 study, which was published in the journal Nature, we discovered that this asteroid shower is the most likely source, more than 90% probability, of the Chicxulub impactor, which caused the Cretaceous Territory (KT) mass extinction event 66 million years ago. However, observation by NASA's Wide Field Infrared Survey Explorer spacecraft in 2011 effectively ruled out the Baptistina scenario by demonstrating that an in-space collision occurred only 80 million years ago or thereabouts. According to the researchers, this didn't give the freshly produced particles enough time to migrate into the position from where one of them could be gravitationally shoved into the Earth-crossing trajectory. We still don't know where the dinosaur-killing asteroid came from. Its parent body is unknown. However, a 2021 study narrows its native neighborhood a little. SWRI scientists David Nesvorn, Bottke, and Simone Marcy employed computer models in that paper to better comprehend the asteroid population and powerful impacts like the one that triggered the KT mass extinction. They discovered that the dinosaur killer was an asteroid that used to be in the main belt, most likely in its outer reaches. Nesvorn and his colleagues also calculated that dark carbonaceous asteroids account for around half of all Earth-impacting objects larger than 3 miles. They discovered that objects at least 6 miles wide are less likely to strike our planet, only once per 250 million to 500 million years. So, fingers crossed another one won't be heading our way for a long time. What's your views on the Chicxulub crater? If you're interested in knowing about asteroids, take a look at our video about Apophis 2029, which is shown here. If you have any topics that you want us to cover, let us know in the comment section below. We hope you enjoyed today's video. If you did like the video, please don't forget to subscribe to the channel and press that bell icon to stay notified. And we'll see you in a new video. Take care.